Good evening. So last class we discussed the PN junction in equilibrium. Fine. So in equilibrium we have seen because of the concentration gradient, there is a movement of hole from p side to n side, and there is a movement of electron from n side to p side. So at the junction we have a depletion width which is almost devoid of carrier. Okay, since we have in the depletion width net positive charge in n side and net negative charge in p side, we have electric field, right? So at equilibrium, this electric field is opposing the further diffusion. Okay, so at equilibrium, there is no motion of carrier from p to n or n to p, because the electric field that is generated, called built-in electric field, is exactly opposing the diffusion force. Fine.
Right, sir.
And also we have seen, because there is electric field, right, there is a built-in potential. Potential is nothing but it is the opposition for the carrier to move from one side to another side, right? And also we have derived the if you see this one, just a minute. Okay, so if you see this one, last time we have derived the built-in potential is nothing but Vt ln Pn by P2. Okay, or if I put P1 and P2 in P side and N side, I got Vt ln N by N square, right?
Right.
Also, we have done the analysis to find out the electric field, and we have got the depletion width h 2 epsilon psi 0 by q 1 by Na plus 1 by Nd square root, right? So, the depletion width is proportional to the built-in potential, also the doping. Clear? Last time we discussed these things. Okay.
Clear.
Also, we derived the depletion width on n side and p side both. Okay. So, this class the things was energy band diagram, forward current, and reverse current. Okay, these things we need to discuss. Okay. So, let us discuss what is happening forward bias. Okay. So, what is forward bias? Right. So, forward bias means when a PN junction, right? PN junction is given a external potential Vd, okay, in which p side is positive compared to the n side, right? Then I can say my diode is in forward bias. Fine. Okay.
Right.
So this is my equilibrium picture, right? This is my equilibrium picture. What will happen if I apply a external bias? Nothing but it is giving a one external potential, external electric field. This external potential, right, causing a external electric field, right? This is called E external, right? So this is my built-in, right? And this is causing a external electric field. I don't know. So what is happening in the junction? The net electric field is decreasing, right? Because the net electric field is built-in field minus the external electric field, right? So this is the net electric field. I don't know.
Right, sir.
So earlier the field which was exactly opposing the diffusion force, that's why the holes and electrons are not able to move from one side to another side. The field have been decreased by the external potential or external field, okay, by amount of E external. Okay, that's why since the field is imbalanced, right, what happened? Because the field is not exactly opposing my diffusion force, there will be some more flow of holes from p side to n side and flow of electrons from n side to p side, because the diffusion force is now more than the drift force. Correct?
Right, sir.
Okay. So you see, this this will cause the external electric field will decrease the electric field. Okay. Since the electric field decrease, okay, what will happen? The holes will flow from p side to n side. The electron will flow from n side to p side. Okay, and there will be a current. Okay, because of the current is nothing but the flow of charge carrier. I don't know.
Yes. Right.
Right. So application of forward bias lower the built-in potential and allows the carrier to cross the junction and result in current flow. Okay.
Right.
Okay. So let us now understand the thing. This is just a qualitative explanation. Okay, let us understand the thing from the quantitative view. Okay, so for that we will switch over to my whiteboard. Okay, before that we want to cover what is called energy band diagram. Okay, what is energy band diagram in a PN junction? Okay, suppose if I give you any semiconductor, how to find out the energy band diagram. Okay, so the today's topic is first topic is energy band diagram. Under equilibrium. Clear topic. Okay, so let us take a semiconductor PN junction. Okay, this is my PN junction. Okay, so this is my junction. This is my junction. Okay, and this is my representation width in equilibrium. Assuming okay, this is my PN junction. Okay, so let us assume that I have P plus N junction. Okay, meaning is P type is little more heavily doped than N type. Okay, this is the condition. Since P type is heavily doped, representation width in P side is less compared to the representation width in N side, right?
Right.
Okay, now I want to draw the band diagram. So what I have to do? Oh, this is my junction. Junction. Okay. See, far away from my junction, right? It is electrically neutral, right? So the first thing, okay. See, Siri, this is my question in interview. Okay, draw the energy band diagram for a PN junction. This question have been asked to me in IIT Kanpur for MTech interview. Okay, they asked me to draw this diagram. Right. So the first step is, since it is in equilibrium, right? The current should be zero. I don't know.
Right.
Zero. Right. So we know the current is nothing but proportional to d f by dx. That is, I derived. Derived or not derived?
Yes, yes, derived, sir.
You remember?
Derived, sir. Yes.
Yeah. Here you see. Here. Next. Yeah. What is that actually? Yeah. Okay. This one, right? So when I add drift and diffusion, right? Both will get cancelled, right? Next we will get what? As a Jn is equal to q mu and dfn by dx. Right or not?
Right, sir.
Right. This is the thing I'm talking about. Okay. So the first step is the Fermi level is constant throughout the device because this implies EF is constant. This is the first step for the Venn diagram. Okay, so first draw a level which is constant for the device. Okay, this is my EF. Okay, after drawing EF, okay, first you just extend this one. In the quasi-neutral region, right? In P set, right? P set, I know the holes are majority carrier compared to the electrons, clear? And I know that in a P-type semiconductor, the Fermi level is near to conduction band or valence band.
Valence band.
Valence band. So draw the valence band here. Okay, this is my valence band. It is closer to the, okay, closer to the, this is my EV, right? If I know EV, what is the distance? EF minus EV in P type, KT ln NC by NA, right? This is what we derived. The difference between EF and EV is this one. We have derived, right? Depending upon the doping level, this can be calculated. If I know EF below, how much below EV means you have to go this much distance below EF to calculate EV. Clear?
Clear.
This is derived. Okay. If I know EV, I have to go up of the energy gap to get the EC. So then from EV I have to go above E. This is my EC. Right? So if you get EV, how to get EC? Okay, you have to go from here, energy gap, just to, this is my EG. If I know EB, I have to go up by energy gap to reach EC, na?
Yes.
Yes. Similarly, in the N side, the Fermi level should be close to the conduction band, right?
Right.
So I will draw depending upon the doping. This is EC. EC. Okay. And the distance is given by how much? You have to remember this one. Not remember, you should know. 80 ln NC by ND. I don't know.
Right, sir.
If I know EC, I have to go below EG to get EV. So from here I have to measure a distance of EG, right, to get the EV, right?
Right.
So this is the way you have to draw the energy band diagram in neutral region. This is my EV. Okay. Now we know since here we have got charges, right? We have got charge, and in the diffusion region we have net charges, right? Here we have net negative charge. Here we have net positive charge, right? And there is electric field. There is built-in electric field.
Yes, sir.
Built-in electric field, right? And there is electric field, and we know the gradient of the conduction band energy or valence band energy is giving me the electric field, right? So here to here you have to join like this. Okay, the gradient of this band will give me the amount of electric field here, right? Similarly, the gradient of the EV also will give me the amount of electric field, right? This is the energy band diagram of PN junction. Clear to you?
Clear.
Okay, so this curvature, right? This curvature depend upon the doping. Okay, how we know from the this curvature, right? How it will be curved, right? It can be curved like this also, right? It can be like curved like this. It can be curved like this. It can be curved like this. Anywhere, right? So which curve is right? Getting what is my question? From here to here, you can join in any number of way, right? Then what is the condition for that? So this curvature is nothing but we know d electric field by dx is nothing but rho v by epsilon, right? So d e by dx equal to rho v is here inside in n side it is nd epsilon, right?
Right.
I don't know, right? And what is electric field? Electric field is nothing but 1 by q dEC by dx, right?
Right.
So if you put here, what you will get? dEC square by dx square, okay, will be proportional to q nd by epsilon, right? I don't know. So the curvature of the curvature of the conduction band. See, dEC square by dx square is what? It is nothing but curvature, right? So what a double derivative of a function gives what? Curvature or not?
Yes, sir. Right, sir.
Right? So the double derivative of a curvature, double derivative of any function is giving you the curvature, right? The more the double derivative, the more the curvature.
Sure, sure.
Okay. Similarly, in P side, same equation I will write. D square EC by dx square is equal to Q Na by epsilon. Okay. So the curvature here will be determined by the doping in P side. The curvature here will be determined by the doping in N side. Clear?
Clear.
This is the question asked to me in IIT Kanpur. Okay. How to draw the curvature? How to determine the curvature? Safe. Fine.
Okay.
So you understand that in IIT interview up to what level the questions are asking people. Okay.
Okay.
Okay. So this is the energy band diagram. Okay. Then we will analyze the ideal IV characteristic of the okay. So what we are going to do, like we have seen here, we take a PN junction. Okay. If we apply a forward bias, okay, this is my I applied a forward bias. Okay. And what I assume, this is my diffusion width. Okay. So first you have to know what are the assumption you have to make. Okay, for deriving the this is P plus N junction. Okay. So what are the assumption first you have to make for getting this ideal characteristic, IV characteristic. Okay. So the first assumption is the boundary between special and neutral region is abrupt. This is my diffusion region. Okay. This is my neutral region. Okay. The first assumption is the boundary between the two is between charge and depletion is abrupt, right? Not gradual. Okay, this is the first condition. Okay. The second condition is P and N regions are uniformly doped. Okay, and width of this regions are the width of this regions are okay. This width of regions are N and P region far more than the diffusion length. Okay, diffusion length. Getting? So you know whenever the holes will be injected from P side to N side, okay, they will diffuse in the N region, right? The holes will be injected from P side to N side, and in N side they will diffuse. The diffusion length. Diffusion length is nothing but the average length traveled by the carrier before they recombine. Getting? What is the diffusion length? So the average length traveled by the carrier in n set before they recombine. Are you getting? Hello? Hello, Siri?
Hello.
Yeah, getting?
Yes, sir. So, what's this boundary between space charge and depletion?
Yeah, see what you're telling. Just after the depletion region, my special is starting. There is no like this. It's not like just after my depletion region, my this is starting. This is the meaning. Getting? Okay. So another thing we are assuming is whatever you applied, right, the VD, okay, it is approximately falling in the depletion region. This is the VD. Okay. So the potential drop in the neutral region is almost zero. Okay. This is the third assumption. Okay. So whatever you are applying the external potential, it is almost dropping in the this region. This is the third assumption. Okay. So with all this assumption, we will try to derive the ideal current voltage characteristic. Okay. So for that, first we will draw. You see, first we will draw the PN junction. Okay. This is a PN junction. Okay. This is my depletion region. See, Srihari, suppose this is my depletion region at equilibrium. Okay. This green correspond to equilibrium. Equilibrium. Okay. So when we apply a potential, right? What will happen to my depletion bit? Srihari? Because you see, when I apply a potential, when I apply external built-in electric field, right? When I apply a external built-in electric field, right? So the net electric field is decreased, right? Net electric field is nothing but built-in minus external, right or not?
Right, sir.
Right. So since the net electric field is decreased, definitely the net charge also will be decreased because field is nothing but charge, right? So the net charge also will decrease, right or not?
Right, sir.
So net charge decrease means the base of the depression region also will decrease.
Yes, sir.
Yes. So what I'm telling, if we apply external potential, right? The net, this is my equilibrium, right? If I go to, this is my condition, and forward because the depression bit will shrink. Idea is clear?
Yes, sir.
So this is red is correspond to forward wise. Okay.
Okay.
Okay. So now at non-equilibrium, what is the so at equilibrium, I have my electric field is like this, right? If I plot x versus electric field, right? Electric field. So my electric field is like this. I don't know. This is my electric field. This is my junction. Okay. This is my electric field. EM. Clear?
Clear.
But when I apply product-wise, the net electric field is decreasing, right? So it will be like this. So suppose actually, this is right. So what will happen? I take product-wise. So it decreased. Okay. So the electric field is decreased. Clear?
Clear.
Here. So earlier the area under the electric field was giving me what?
Voltage.
Earlier the area under the electric field was giving what?
Potential. Built-in.
Potential. That is high built-in, right? Or I was repeating psi 0. Okay. Now the area under this electric field will given be what? VBI minus V applied or V bias, or I can say VD. The area under this electric field will be given by VD. Clear?
Okay, sir. Is the forward bias is more than built-in potential than VD
No, no,
minus?
no, no. That is a completely wrong concept.
Okay,
Completely
okay,
wrong
okay.
concept. See, what I want to decrease the electric field, not zero, right? Even if little bit decrease also, right? The balance will be gone. The holes will move from P side to N side and N side to P side. Okay. In fact, I cannot make this electric field zero.
Okay, okay.
If you think that it should be exactly like if you are thinking that VD should be greater than VBI, you are absolutely wrong.
Okay,
Okay.
okay, okay.
So in fact, when we apply VD more than VD more than VBI, right? What will happen, right? This extra potential will drop in the junction. This contacts. Okay. But the across this depletion width, it will be always less than VBI only.
Okay, okay, okay.
Fine. Huh? So I want to reduce the balance. Earlier the electric field was balancing. Now I decrease the balance so that there is a flow of holes from N-side to P-side. Okay.
Okay, sir.
Okay. So suppose suppose in equilibrium there is a, suppose I want to draw the, see, suppose I want to, in a log scale I want to draw the whole concentration. Okay, this is P plus this is N. Okay. So in P side the holes are, this is my whole concentration, suppose. Okay, this is PP0. Okay, this is my PN0, right? Because I have applied a forward bias, right? The electric field is reduced. What will happen? There will be injection of holes from P side to N side. If you see, this will be this will increase. This is nothing but my PN. In forward bias, this PN0 will more because it have been injected from P side to N side, right? Understand or not?
Just one second, sir.
Pardon me.
Sir, could you explain that once more?
See, earlier I have got PN0. Okay, PN0 is the minority carrier concentration at equilibrium in N side. Okay. Now, after the application of the external potential, external electric field, the field is imbalanced. The opposition force, opposition electric field decrease. So there is injection of hole from P side to N side. So if you see junction, the number of minority carrier which was PN0 will be increased. So it is PN. PN is nothing but the whole concentration in non-equilibrium.
Okay, okay, okay.
Fine. So
Clear.
yeah, if I want to draw in a like diagram, right? What will happen, right? So you see, if I want to draw a flow diagram, okay, what will happen? The holes, right, will be injected from P side to N side. Okay, this is the hole. Holes will be injected from P side to N side. Okay. Now, since in the N side, right, N side, I have more number of holes, right? So what will happen? This contact, right? This is contact. This is a contact. Then I have applied a potential, right? This is a potential.
Sir, the left side PN0 also I mean, PP0 should also get down, right, sir?
Why?
Here on the right side, PN0, it has raised a little bit more.
No, I will explain. Wait. Just wait. I will explain you. Okay. So you see, the holes have been injected from P side to N side. Okay. So this is my hole injection, right? Then I will have what? Okay. Then I have more number of holes in the N side, right? Compared to the electrons. Right or not?
Right.
Right. But it is not possible, right? Because these are electrical neutral, right? Since holes are injected from P side to N side, I have more number of holes, right? What will happen? This contact, right? This contact will inject electron, right? And it will recombine with the holes. These are the electrons, okay?
Okay.
Let me drop another color. Okay. Since there are more number of holes, right, in the N side, right? This contact will give the equal number of electron so that they will go and recombine with the holes. Okay. Okay. So what will happen? This contact will inject electron, okay, and they will recombine with the hole. Getting?
Getting.
So since it is electrical neutral, the holes have been injected from P side to N side. We have more number of holes, right? And the more number of holes, they will recombine with the electron that will be injected by the contact. Okay. Similarly, because of the electric field is reduced, the electrons will be injected from N side to P side. Okay. And since the electrons are more in P side now, what will happen? Again, the contact will inject the hole. Okay. They will recombine with the electron. Clear? Okay. So this is the contact. This is the contact. This is the contact. Okay. So you see see whatever holes will be injected, right, from P side to N side. Okay. The equal number of holes will be injected by the contact from contact to P side here. Okay. So we are thinking that the PP0 will decrease, right? So it's not like that. So whatever will be injected, they will be replaced by the injection of holes from the contact. Okay.
Okay. Okay.
So the contact will give holes. Some of them will be recombining with the electrons which have been injected from N side to P side. You should again see what I'm telling. The contact will inject hole. Okay. Out of that, some of them will be injected from P side to N side. Okay.
Okay.
And some of them will be recombining with the electrons that have come from N side to P side.
Right.
Okay. Similarly, here also the electron will be coming from contact. Okay. And some of them will recombine with the holes that have been coming from P side to N side, and some of them will be injected to the P side. Okay. So because of the imbalance in the electric field, there will be injection from N to P and P to N. Okay. But that will be given by the contacts. Ready?
Right.
So this is the flow of electrons and holes in the Faraday device. Okay. So now you understand that in Faraday device, I have got extra number of holes in the N side, nothing but magnetic area, right? Extra number of magnetic area in the N side, and I have got extra number of electrons in the P side. Right or not?
Right.
Right. And the electrons are magnetic area in P side, and the holes are magnetic area in N side. Clear?
Clear.
Clear. So now what will happen? You see, there will be interesting thing will happen. Okay. Now what will happen? This Pn, right? What is this value of Pn? Now my question is, since Pn have an increase from Pn0, right? So there will be change in the magnetic area concentration, right? This one. Okay. What is this delta P? Okay. The question is, if I applied a electric potential externally, okay, there is change in magnetic area concentration at this. Yes. Also there will be change in electron also, right? So if you plot the electron also, it will be similar, right? So it will be Okay, the electron charge will be more here. Okay, there will be change in delta n in p side. There will be change in delta p in the n side. Okay, so what is the change in the junction? That is my question. Okay, getting?
Okay,
Hello?
okay then.
Yeah.
Yes, sir.
So for that we will use our concept. Okay, what is the concept? We know, like we have explained you last time, right? The building potential is given by, okay, Vt ln P1 by P2. I don't know.
Right.
So what is VBI? VBI is equal to so we know VBI is equal to VBI is equal to Vt ln P1 by P2. Right? Surajit, are you there? Hello? Hello, Surajit? Surajit?
I think its audio is not connected.
He is not connected?
I think its audio is not connected.
Okay, okay. Okay, okay, fine. So I think he will be connected. I think some network issue is there, right? Okay, we'll see. Surajit, are you there? Surajit, Surajit? Okay. So Siri, Siri, you are audible?
Yes, sir. Yes.
Okay. So what are you telling, right? The built-in potential, right? P1 bit. Okay. So equal to Vt ln what is P1? P1 is the concentration of hole in the P side. Okay, is equal to P0. P0, right? P2 is nothing but concentration of hole in the n side, right or not?
Right.
Pn0. Okay. So if I write like this, what will happen? P0 by Sujit, Sujit, are you there? Exponential of dV by Vt, right? Right?
Right, sir. Right.
Right. What is Pn0? Pn0 is the concentration of magnetic carrier in n side equal to P0 divided by exponential of dV by Vt equal to P0 into exponential of minus Vbi by Vt or not.
Right.
Okay? This is the condition. Okay. So with this equation, we will try to get the Pn0. Hello, Srijit, you are there?
Yes, sir.
Srijit, audible?
Network issue is there actually.
Pardon? Network issue there. Okay. So what actually, let me brief you. What we are telling. When you apply forward bias, right? This will this will this will create a external electric field. Okay, that will oppose the built-in electric field. So the net electric field will decrease. Okay, because the electric field decrease, the opposition force also decrease. So the earlier the electric field was balancing, now the balance have gone. So there will be a movement of holes from p side to n side and electron from n side to p side. So there will be a current. Getting, Srijit? Okay, and if you see in forward bias, the net potential across this junction will be Vbi minus Vd. Okay,
Yes, sir.
and see what happen when we apply forward bias, right? The holes will be injected from p side to n side. So at the junction, you will see there is an increase in hole concentration. Similarly, the electrons will be injected from n side to p side. At the junction, I have a more concentration of electrons than in equilibrium. Okay, so you see, we have given a flow diagram, right? So the holes will be injected from p side to n side. So in n side, I have more number of holes. Okay, but we know it should be electrically neutral. So the contact will inject electron and it will recombine with the holes. Okay. Similarly, the electrons will be injected from n side to p side and will be given by the contact. Clear? This flow diagram is clear? Okay. Now I want to derive a equation for the increase in concentration at the junction. Okay. So now this is the equilibrium, right? This is the equilibrium. So is it clear? Okay. Now at the forward bias, the potential is now V minus VB minus VD, right? This theory?
Yes, sir. Yes.
Yes. Now what will happen? If I go to, so when I apply a forward bias, in forward bias, what will happen? If Pn0 will be Pn equal to Pp zero exponential of minus, instead of VBI, I have VBI minus VBI minus what?
VD.
VD by VT. Okay. So it will be Pp0 into exponential of minus VBI by VT into exponential of VD by VT. Okay. So we know Pp0 exponential minus VBI by VT is nothing but my Pn0. Okay. Pn0 into exponential of VD by VT. Right, Sherry?
Right, sir.
So what I can write? The concentration at the junction in forward bias equal to whatever it was there will be increased by exponential of the applied potential. Here. Clear? Okay. So this is the net thing. So what is change? Change is equal to del P is equal to Pn minus how much it was there already. Okay. So I will get Pn0 into exponential of Vd by Vt minus 1. Right? This is a change in concentration. Here, so is it? Here is clear?
Clear.
Yes. So if I want to represent this del P, what is the change? Change will be how much it was there, Pn0 into exponential of V by Vd by Vt, right? Minus 1. I do not.
Right.
Right. So it is this exponential increase in concentration is giving me exponential current voltage characteristic. Clear? So depending upon the potential, the concentration at the junction varies exponentially with the voltage. Right?
Right, sir.
Right. And one more thing I'm telling you. You see, at equilibrium, I have VBI is equal to Vt ln Vp0 by Pn0. Right? Pn0. Okay? If I go to third bias, the potential will be VBI minus Vd. I don't know.
Right, sir.
Into Vt ln Pp divided by Pn. Here, since this is decreased, right? This is decreased. Definitely, Pn have to be increased. I don't know.
Right.
Right? So, and Pp0 also have to be decreased. But anything can happen, right?
Right.
Okay. So, are you getting?
Yes, sir.
Oh, great. So, have you got this flow diagram? The flow diagram you understood? So, is it? Have you understood this flow diagram? Okay, let me. So what I'm telling, this PN0 is increasing, this is decreasing. Okay, and actually, if you see, here, right, here, whatever amount of increase in electrons are there, same amount of increase in holes will be there, right? Because this has been coming from the contact, right? Here I told you.
Yes, yes.
Here also, how much amount of del P is there, same amount of del Ln will be there, right? Because it has been injected from the contact. Okay, but here, if you see, the net concentration will be, so for net in N side, if I say net electron concentration, okay, Nn equal to Nn0 plus del N, okay, del N equal to del P, or del P. What is that? This Nn0 is far greater than del P. Ready? So I can write Nn equal to approximately equal to Nn0. Clear, Sherry?
Yes, sir.
Clear. So here I can write Vt ln Pp will be almost equal to Pp0, right? Because it will be equal to Pp is actually equal to Pp0 plus del N. Okay, del N is nothing but the electron injected from the N side. So how much amount of electron will be injected from the N side? Same amount of hole will be injected from the contact. Clear?
Right, right.
So the total Pp0 will be Pp0 plus del N, right? Okay, so it will be approximately equal to Pp0 only, right or not?
Right.
But Pn0 will be equal to Pn0 plus the del P. Del P is nothing but Pn0 into exponential of that one, right? So it will equal to Pn0 plus del P. Okay, del P. Del P is nothing but this one I have given. This is del P. Clear? And which cannot be neglected. I don't know. So what I can say, if I go to forward bias, the minority carrier concentration is increasing. Shall I like this? Sherry?
Yes, yes, sir.
It is clear?
Right, clear.
Clear. So now I got the minority carrier concentration at the junction. Okay. Then I have to know how it is there inside the neutral region, right? So what I have to know. So are you getting? Okay. So if I want to draw, okay. The electron, no, this is P plus N junction. Okay. If I want to draw the electron and hole concentration, okay. This value I know, right? That's right. Okay. What is this value? Theory? What is this value?
Pn,
Huh? If I want to plot only the extra concentration, okay. What is this value?
delta
Delta P equal to Pn0, okay, into exponential of V by Vd by Bt minus 1. Right? Right or not?
right,
Right.
right,
This I
sir.
know at the junction. And if you go and solve the equation. Okay, if you see inside this, okay, it will vary exponentially like this. Okay. This is the profile of the concentration inside the neutral region. Okay, so how to get this? You have to go to the continuum equation. Okay, for that, what I'm telling, what you have to do, you have to go to the continuum equation. Okay, what is continuum equation? Del P by del T is equal to minus del P by del T equal to minus 1 by Q dj by dx plus G minus del P by tau. Okay, getting? Okay, here, and I'm assuming now inside this N region, right? The holes are majorly moving because of diffusion, because there is a concentration gradient, right? Majorly they are moving because of diffusion. Okay, so this J will be approximately equal to J diffusion only. Okay, and since I am in steady state, this will be 0, right? Clear? Hello?
So why is it 0, sir? I
Because I
haven't
am in
heard
steady
it.
state. See, we are discussing the steady state condition.
Okay, okay, okay.
It is 0. Okay, there is no generation here. It is 0, right? Because these have been injected from P side to N side, right? The holes have been injected from P side to N side. This is not generated, right? Here, I do not.
Right.
Right. So if you put all this, right? If you see minus 1 by Q d, the J is nothing but diffusion only, na? Okay, I am assuming because of diffusion only. Okay, it should be actually diffusion plus drift. But what I am assuming, the holes are moving only because of diffusion, right? Because there is a concentration gradient, right? So dx equal to minus equal to del P by tau. Okay, so what is diffusion? You know, minus 1 by Q dj by dx. What is diffusion? We know Q dp by dx. I do not.
Right.
Huh? Right? Q
Negative,
cancel. Right?
and
Okay.
negative is there also.
There.
Okay, okay.
Ah. No. Yeah, negative is there. So negative cancel with positive. Okay. The negative and the diffusion negative will get cancelled. It will become positive. Okay.
Okay.
So d square dy dx square equal to del p by dp into tau p. Clear?
Yes.
Okay. The dp and tau p is called LP square. Okay. LP is nothing but diffusion length. Diffusion length means approximately the holes will recombine after traveling a distance of LP. Okay. So I got L square P by Ls square del P by LP square. Clear, Sherry?
So in the last class, you asked me to remind this
Yeah.
form.
Same thing. That's why I explained you this one. Okay. Diffusion length is nothing but root over dp into tau p. Okay, from this here. Okay. So this two thing I'm just taking as a constant LP square. So this LP is nothing but every distance traveled by the holes before they recombine. Okay. This is
How
called
that
diffusion length.
how that came actually this
No,
root.
see, this is the equation, right? If you solve this equation, so see, I'm just denoting this one as a another constant as LP square.
Okay, okay.
This equation is confirmed, right? This equation you understand, right? This equation.
Yeah, sure,
Okay.
sure.
So dp and tau p, I'm just denoting as LP square.
Okay. Why
Okay.
LP
Why?
square?
I will tell you. Because you see, if you solve this, right? If you solve this equation, right? You'll get del p is approximately equal to, okay, something I did not remember exactly. Del p, sorry, uh, del p equal to pn0 something, okay, into exponential of, I'll get del p is equal to del p into exponential of, okay, minus xc by lp. What I'll get? If you solve this is a second order equation, okay. If you solve this, you will get del p of x, okay. Del p of x is equal to del p is nothing but concentration at junction, right? Junction into exponential of minus xp x by lp. Okay, so if you see approximately they will decrease to e to the minus 1 traveling distance of lp. Okay, so if you plot this one, it will be like exponential. Okay, so over a distance of almost lp, okay, they will almost decrease to 0, not 0. I can say they travel approximately lp distance from this expression. Okay,
Okay.
this is where this I tell is a diffusion length, because mathematically it comes minus x by lp. If I denote it lp square, right, then if you plot this equation, okay, they will come to lp power of lp into at this point. Suppose see, if you plot this, right, if you plot this x versus this one del px. So are you getting, Surajit?
Yes.
Oh, great. So the del px if I plot, right, it will be like exponential. Okay, if I say at lp, x equal to lp, what is the concentration here? It will be lp into e power of -1. I don't know.
Right.
Okay. So I assume that almost they are decreasing. They are combining, traveling at a distance of lp. Okay, that's why it is called diffusion length. Okay, fine.
What's the significance of that diffusion limit?
So diffusion length is nothing but they are approximately decreasing to e to the -1 after traveling a distance of lp.
Okay, like we can say like skim depth or something similar to that. One by one by.
Pardon me. Yeah. So also you see, if you find out the if you find out the suppose if you want to find out the just a minute. Okay. If you find out the slope of this, right? Slope of this at x equal to 0. Okay. What is the slope of this? Del px slope by dx equal to del p by lp, right? Into exponential of minus x by lp. I don't know. Minus, right? Right now. So
Right.
if you find out the slope of this at x equal to 0, okay, at this junction will be equal to del p by lp. Na?
Yes.
Slope here is exactly equal to del p by lp. It's like so this the current at t equal at x equal to 0. Okay, so the current at x equal to 0 is dp by dx at x equal to 0. Okay, will proportional to del p by lp.
Right.
Right.
Right, sir.
Right. So this lp is nothing but a averagely a diffusion length. Average they will diffuse. Okay, beyond lp, the diffusion current will be almost very small.
Okay.
Okay.
But sir, in
Okay,
expression of del p,
Yeah.
in expression of del p, it should be e to the power minus xn by lp, because
Yeah. So,
the
that's
area
right.
will be generated
Here I
at
am
the
assuming
end
that
of
x
xn.
is equal to 0. Okay. But if you put x equal to xn here x minus x1 will come. Na? Ready? I'm just giving you an example of here x equal to 0 I am putting, right? If you put x equal to xn, here, suppose if you put x equal to xn, here x equal to, this is x equal to 0, right? You say, this is
Okay.
x equal to 0. Okay, this is x equal to xn. Okay. So if you do like this, then this, so what you want? You want it x equal to xn, you want del p, right? And
Yes,
it will go. So what the equation will be? Actually, this will be del p exponential of minus x minus xn, okay, by lp. So that
yes,
at x is equal to xp
sir.
xn, I'll get del p, right? Then it will decrease exponential. This is just shift, it will shift, right? But again, the slope at this is equal to del p by lp only. I don't know.
Yes, sir.
Yes. So you understand that key, this will be exponential curve. Okay, I just give you a rough estimate of why it is exponential. Okay, I did not did a detail derivation. For the time constant, I did not give a detailed derivation, but just to want to give you why this whatever holes have been injected, how it is exponentially decaying inside the n region. Okay, this is because of the continuity equation which I derived. Okay, here you have to put this equal to 0 because it is steady state, and there is no generation here. You put this, you will get the expression is exponential. That's what I want to mean you. That's what I want to take from this slide. Okay. So they will decrease exponentially in this n region. Here. Hello. Hello. Is clear or not clear?
Yes.
What I'm telling?
Yeah.
Whatever holes
Yes,
is
sir.
injected, the value of holes is del Pn0 into exponential minus 51. Okay. And they will decay exponentially. Okay. According to this relationship, this one. Okay. Del P into exponential extension by LP. Okay. Similarly,
Clear.
in P side, the electrons will be decay like this. Okay. And this point will be how much? This point will be ln equal to n P0 into exponential of V by 50 minus 1. Right? Theory?
Right, sir.
Getting? Okay. So, what all I'm telling, in forward bias, the holes will be injected from P side to N side. The electrons will be injected from N side to P side. And it will follow like exponential. So then after injection, they will diffuse. Okay. So when because the concentration more here, right, compared to the at this end, so they will diffuse. While diffusing, they will recombine. Okay. So since they will recombine, the concentration will go on decreasing as you go along the n region. Similarly, electron after diffusion, they will diffuse, and while diffusion, they will meet with the electron and they will recombine. So their concentration will go on decreasing, and it will decrease in an exponential manner. That's what I mean. Fine.
Fine.
Fine, Surajit. Okay. So now, since you know it's steady state, right? In steady state, I told you, right? The current is constant for a device. I don't know.
Right.
Right. So, and at any point, right? At any point, suppose at this point, at this point, I want the current. Okay. So I want both current is equal to current due to holes plus current due to electrons, right? At any point.
Right.
And I know the current is constant throughout the device. Okay. If you want to find the current here due to holes at this point, what do you have to do? The current here is how much? Jp is equal to minus q dp v by dx, na?
Yes, sir.
By dx. Okay. So since the del p is exponential, if I want to plot the current due to diffusion because of holes, it also will be exponential, right? Right? This will be Jp in n region, right or not? So Suraj Srirari, right na? Okay,
Right.
because since this is exponential, if I derivative it also will be exponential. Okay, and what is the value here? The value here is okay will be equal to what is the value here? Value here I know the slope is nothing but dp by dx slope is nothing but given how much? Del p by lp na? I given the slope is nothing but del p by lp at x equals 0, right?
Yes, sir.
Share it, right or not?
Right. Right.
If I derive it at x equals 0, so what is the slope? So if I is like this is like suppose lp. Okay, what is the slope here? Slope is nothing but q into dp del p by lp. Okay, this is the current at this point because of the diffusion. Clear? And if I assume there is no recombination in the depletion region, the same current I can say flow like this. This is my Jp, right? This I can say my Jp. I don't know. Similarly, here if you see this current, okay, if I want to plot the current due to electron in NP side, it also will be exponential, right? And the current here exactly at this point will be how much? Will be Q dN, right? Del N by Ln. Okay, here LP is nothing but root over of LP is root over of
BP.
dp into tau. What is Ln? Ln will be equal to dn into tau n. Similarly, I don't know. Okay, so this is the current, and since I assume that there is no combination inside the depletion region, so the same current will flow in the depletion region. Okay, this is my Jn. This is my Jp. But what is the total current in the depletion region? It will be Jn plus Jp. This will be nothing but, right? The total current at any point will be current due to electron plus current due to holes, right? Surajit, theory. Okay, and since the current is constant throughout the device, so the same current will flow through the device. Clear? Fine.
Fine.
Fine. If I want to find out the current due to electrons in the N region, right? What will be? It will be total current J minus Jp.
Yes.
Fine, na?
Fine.
Fine. So total current J minus Jp. So it will be how much? It will be. To take okay. My current due to is my Jn, right? And if you see, if you go little far from the junction, okay, the diffusion current due to holes will be decreasing, and the current due to electrons is increasing. I don't know.
Right.
And similarly, if you see, this is my Jn, okay, if I want to plot the current due to holes in the P region, it will show J minus Jn, so it will be like this. This is nothing but my Jp in P region. Clear? So this is my Jn, this is my Jp, this is my Jp, this is Jn. Is it clear? So just
Clear.
total current minus the electron current is nothing but whole current.
Clear.
So this is clear very much. And one more thing, like I showed you in the flow diagram, right? Flow diagram, the electrons are injected from the contact, and the electron current is nothing but shown is here. This is my electron current, okay, which I showed is which have been injected, okay, which will maintain the equilibrium, which will maintain the neutrality, okay, because it will recombine with the holes, and also the electron will be injected from N side to P side, okay. So what is I am claiming here? You see, the electrons are, you see, the whole current, if you see, is because of diffusion inside in N region, right? The whole current is because of diffusion in N region, right or not? Hello? Hello?
Hello. 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 Sir.
Yeah, the whole current is because of diffusion in N region. Clear?
Yes. Yes.
Similarly, the electron current is because of diffusion in P region. Okay? I don't know.
Right.
Right. Now, this electron current in N region is because of drift. Drift. Similarly, this whole current in P region is because of drift. Getting? And this is injected by the contact. Okay, the contact will inject the electron. Some of the electron will combine with the holes, and some of it will be injected to the P side. Is this picture clear to you all very much?
Clear. Clear.
Surajit, is there any doubt at this point? Surajit? Okay. So Siri, what is the total current now then? total current is nothing but equal to, okay, this current Jn plus Jp, okay, what is Jp? Jp is nothing but Q del P by Lp, okay, Q dp Lp by Lp plus the electron current here Jn is nothing but Q dn del n by ln, Q dn ln by ln, right? So this is the total current, right? Equal to Q dp. What is del P? Del P is nothing but Pn0 into exponential of G by Vt minus 1 by Lp plus Q into Dn. What is del n? Del n nothing but n P0 into exponential of minus 1 by Ln. Clear, theory?
Yes.
Clear. So what is the current? Q dp into Pn0 by Lp plus Q dn into Np0 by Ln into exponential of V by Vt minus 1. Clear?
Clear.
This is the total current. Okay. So, shall we have to remember this equation? Theory. You see, right? This you know. The current is because you should in your mind you should think. Okay. We have got the current. Adding these two current. Right. This current you know del P by Lp. Proportional del P by Lp. This can depend upon del N by Ln. Okay. We know del P. Del P also is equal to Pn0 into this one. You understand this one. And del also you understood. Okay. So this is this thing you put here. Then shall we have to remember this equation? So one component is because of holes. This component is because of electrons. Right? This is my total current. Right?
Right.
Shall we have to remember this one? Hello? Okay. If I want current, I have to multiply by area. Area. Okay. This is my current ID. ID equal to this into area. I have taken as a I0 into exponential of d by Vt minus 1. Okay. Hello?
Clear, clear, sir, clear.
So what is I0? I0 is this one multiplied by area. Right?
Right.
Okay.
Right.
Okay. So there is a question for you. What is I? D equal to I0 into exponential of G by Vt minus 1. Clear? So this is an interview question to you. If temperature T increases, ID will increase or decrease? You understand the question? Sir, you understand the question?
Yes, sir, yes, sir. If temperature will increase,
So,
to find ID increase or decrease.
yeah. So can you tell me? Can you tell me? Okay. So let me tell you one thing. Siri, are you there?
Yes, sir, yes.
See, if I increase temperature, what will happen to Vt? What will happen to Vt? Huh?
It will increase, sir. KT by Q.
Yeah, it will increase. And what will happen to this exponential term? This one?
Decrease.
Decrease. And what will happen to ID?
Should decrease.
Decrease. Okay. So is this right? So is this right? Is this right? I think so. Is left. Okay. So Siri, this is the question asked to me in interview. Okay. From this expression, if you understand the expression blindly, just take I0 into S1 minus 1. Okay. Then if temperature increases, current decreases. Okay. But you know, a diode current increases if you increase temperature. I don't know.
So that current, I haven't heard that.
Increases if you increase temperature. Okay. If you maintain the same potential. But from this expression, it looks like it's decreasing, right?
Yes, sir. Yes, sir. I was thinking like that. Due to generation, all those things, I was simply
Yeah.
thinking. Yeah.
You should think it is a physics course. This I0, right? You are forgetting this I0. I0 is proportional to Pn0 and Np0. Okay. This I0 is proportional to Np0 and Pn0. And Pn0 and Np0 proportional is equal to proportional to Ni square. Right?
Right.
So this Ni will increase temperature. Okay. So this I0 also will increase a lot. So the second part, this decrease, okay, is much more less than that in this increase.
Right.
Getting this I0 increase. So the I0 will increase much more than this second part. Okay. Net current ID will increase. Getting?
Right, sir.
Getting?
Getting it.
Okay. This is the trap people will put you.
Sorry, sir.
This is a trap I'm telling. This is a trap I'm telling. This is a trap. Okay. So with this, you have got the understanding of how current flows and what is forward bias. Is it clear?
Clear, sir.
So now shall we go to reverse bias?
Sure.
Yeah. So we'll go to reverse bias. So we have understood how the current flows in the forward bias, right?
Right, sir.
That will go to the reverse bias. Can you see my screen?
Yes.
Okay. So what will happen in reverse bias, right? In reverse bias, we will apply the P type more negative compared to the N type, right?
Right.
What it will do? It will increase the external electric field, right? Earlier the built-in electric field is like this. This is my built-in electric field. Okay. Earlier this was my built-in electric field. Okay. Then I have increased the electric field more. This is my external electric field. Right? Because here it is positive, here it is positive,
Yes, sir.
here it is negative. Right? So it is external. So total field is nothing but E plus E external. Right? So, so the barrier for the hole to flow from P to N, the barrier for electron to flow from N to P is increased.
Yes, sir.
I don't know. But
Right.
what it will happen? This electric field, what it will do, right? Even though the barrier for the holes, right, from P to N is increased, but the electron can flow from P to N, right? Because now the field is more. It will allow, because the force is more for the barrier is like that. This is the barrier. Okay. But this barrier opposes the flow of holes from P to N. This barrier opposes the flow of electron from N to P, right?
Yes, sir.
But this barrier is supporting the flow of holes from N to P. I don't know, because this electric field can push the holes from N to P, no?
Yes.
Similarly, this barrier support the flow of electron from P to N.
Yes, sir.
Huh?
Like contacts also repel these electrons.
Yeah,
Right.
that's what I'm telling. The barrier is supporting the electrons flow from P to N, supporting the whole flow from N to P. Right? So the electron can flow like this, holes can flow like this.
Sure.
Right or not?
Right.
Right. So since the electron will flow like this, holes will flow like this, the current will flow from N to P. Earlier the current will flow from P to N. Right?
Yes, sir.
Okay. But the issue is what? Issue is even though the electric field is supporting the flow of electron from P to N, electron flow from P to N, even though the external electric field is supporting the flow of holes from N to P, but you have very less number of holes in N region, very less number of electrons in the P region. Okay. Even if the field is supporting, but I don't have electrons in P region, I don't have holes in P N region, they are very, very small, right?
Right.
Right? So that's why the current in reverse bias is very, very small. Because even though the external electric field is supporting the flow of electron, but they are very, very small. Finally, the holes are very, very small. That's why the current is almost constant. Okay. If you see this expression, I is equal to I0 exponential of V by Vt minus 1. If you go to very high negative, right? If V is equal to minus Vd, right? So it will be equal to I0 exponential of minus Vd by Vt minus 1. Right? So if Vd is little bit more, far more compared to Vt, then this will be almost 0, right? So my current will be approximately equal to minus I0. So it is opposite of the current flowing in the forward bias, and it is almost constant because I don't have much number of carriers. Even though the electric field is supporting, the carrier is limited. So how much carriers are there, they will travel, and that is constant because the carriers are very, very small, right or not?
Right.
Right. So this will happen in reverse bias. The current is very, very small, approximately minus I0, because it is limited by the number of carrier in P side, number of carrier in N side. Okay, that's why it is called reverse saturation current. Okay.
Okay.
Okay. So because very few electrons in P side, okay, because very few electrons in P side, very few holes in N side, the current in reverse bias is very small. Here.
Yes.
Here. Now you see, since since the external electric field is increased, right? So we have to uncover more number of charges. Na? Definitely the positive charge here should be increased. The negative charge here should be increased. Right? I don't know.
Yes. Yes.
Yes. What does this mean? So the diffusion bit will increase.
Sure. Sure.
Okay. So if you go on increasing the reverse bias potential, the diffusion bit will increase. Clear?
Clear.
So since the diffusion bit will increase, the positive charge will increase. Here the negative charge will increase. Okay.
Okay.
So if I increase the reverse potential, the diffusion bit is increasing. Okay. The xt difference bit is increasing. Okay, so the number of charge is increasing, right? So it is giving you giving you a capacitance, nothing but change in charge by change in potential, nothing but capacitance, right? If I change the external potential, it is a change in charge, right? So what is my capacitance? Capacitance nothing but change in charge by change in potential. I don't know.
Right. Right.
Right? So this is going to give me a capacitance that is called depletion capacitance. Fine.
Okay.
So in reverse bias, if you draw, right? This is your junction. Okay. At equilibrium is your right. Right. If we apply reverse bias, right, what will happen? Your representation will increase. Okay. Will increase. Right. So this is correspond to equilibrium. This correspond to reverse bias. Okay. If I apply a reverse bias, E and N. Okay. Reverse bias. Okay. And representation will increase. Clear?
Clear.
Clear. Since representation increase, represent charge also will increase. Okay. The change in charge in represent region for the change in reverse bias potential is giving you a capacitance that is called represent capacitance. Fine. Okay.
Fine.
So what is represent capacitance? So what is the change in charge? Suppose this is your action. Okay. If we apply reverse bias potential, it is increased by d action. Right. Similarly, this is your xp at equilibrium. If you increase the potential, it is increased by a factor of dxp. Fine. I don't know.
Fine.
So what is change in charge in this d action in this region? So dq is equal to how much in this region, right? In this region. So the change in charge equal to how much it will be? Okay. The concentration E into ND into d action into area. This is for volume into volume. Volume is nothing but distance into area. Area is unity, right?
Right.
Right. So this is the change in charge, right? So what is my capacitance? C depletion equal to dq dash by dvr. I do not.
Right. Right.
Right. So equal to E ND into dq dash by this means dxn by dvr. Fine.
Fine.
You are getting everything now?
Yes, I am.
Okay. This is my capacitance. Okay. So now the derivative of this one will give you the representation capacitance. Okay. So now we know xn equal to 2 epsilon VBI plus VR. Earlier it was only VBI, right? When my field is increased, it should be VBI plus VBR, right?
Yes, sir.
Into NA by ND into 1 by NA plus ND NA by ND by 1 by NA plus ND by 2. Right or not? Okay. So then you have to do dxn. You have to do dxn by d VR. So you have to derivative this expression with respect to VR, right?
Yes.
And after derivation, after derivative, you have to put this value here. Okay.
Right, sir.
Fine. So then you will get the representation capacitance. Okay. So how much you will get? So that this you can do now, or I have to do? This you can do, right?
Clear?
This thing this you can do, right? The derivative you can do, right?
Yes, sir.
The derivative you can do now.
Yes, sir. Treat everything as constant other things and just
Only thing is this you have to derivative with respect to distance. Okay. So then if you see, I'm just writing the final formula. Okay. So C depletion, right? It will be equal to epsilon s by definition bit. Okay. You prove this in your home. Okay.
Okay.
What is XD? What is XD? XD is equal to root over of 2 epsilon VBI plus VR by Q 1 by NA plus 1 by ND. Okay. If you so this is like parallel plate capacitor separated by distance XD. Okay. So this is my XD. Okay. So if you do this derivation, okay, you will get C depression is equal to epsilon S by XD. XD is nothing but my depression width. Fine.
Fine.
Right. So if I want to express, suppose if I put this one here, okay, you get the epsilon S NA and D, NA and D, right? Divided by 2 into BR, right? Okay. This is the expression you will get.
Okay.
Fine. Okay.
Fine.
If you go home and you can do this derivation. Okay. If you don't get, you let me know.
Okay.
So this depression dependent you understand. The inner capacitance.
Got the
Yeah.
approach, right, sir?
Yeah, you got that. That is the only important thing. Okay. Nothing else I want. I want only this one. Okay. So
Okay, sir.
one more thing before I want to wind up the subject, this diode chapter, there is 20 minutes set. So I will take two things. One thing is what is a small signal model. Okay.
Okay.
So you know the diode, right? This is my VD, this is my ID, is exponential. Right? So there is a diode. Right? You apply a potential VD. If you go on increasing VD, right, you measure the current ID, right? It will follow this curve, exponential. Fine?
Fine.
Fine. Suppose for some particular VD1, a current is ID1. Okay. Suppose your current here it is VD1, the current here is ID1. Fine?
Fine.
Okay. What is my question is, they have come in the gate several number of times. If my VD is increased by a very small amount, del VD, very small. Okay. So how much the current will increase? What will be ID? Okay. So then ID also will increase. Right? So what is this change in ID? If my VD is increased by a change by del VD, how much is my ID? So if my VD will decrease by some small amount, how much your change in ID? Okay. So if my VD increase or decrease, I know VD1 for a current, for a voltage VD1, you know the current ID1. Fine.
Fine.
But I'm asking, what is the current for when my VD change by small amount del VD? Okay. So what you have to do? This is called small signal approximation. What you will do? Even though it's exponential, if my VD is changing very small, I will approximate this curve as linear. This is nothing but my small signal analysis. Okay. So even though my curve is nonlinear, exponential, if my change in VD is very small, so like for the small portion of this curve, I can approximate as a linear curve. I don't know.
Right.
Right. And this small signal approximation will depend upon at what point you are. Suppose you are at this point. At this point. Okay. So suppose this point is VD2. 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 And now you apply same small VD. Okay. The change in current will not be same. Right. Suppose you are at a VD1. Right. You apply a small change in VD del VD. Then you note the change in current. Okay. It will be different when you are at VD2, apply the same voltage. Okay, it will not be same change. So how it will depend upon which point you are. At this point, if you want to approximate a linear curve, it will be like this, right? Right. The slope of this linear is different from the slope of this one, no? Right?
Right.
Right. And the slope depend upon what? At what point of the curve you are in. right?
Right.
And that point is called operating point. Okay, the small signal gain will depend upon the operating point. The change in current LVD. Okay, so here it will be more, right? Here it will be more. For the same change in VD, the change in current will be more here, right? So
Right.
the change in current will depend upon the operating point where you are. Fine.
Fine, sir.
Fine. So then now I want to calculate how it will change. Okay. So I know my current I is equal to I0 into exponential of dy dt. Okay. So -1 is there. I am ignoring -1. Okay. Fine.
Fine.
I want to know di by dv. Okay. Is equal to I0 into exponential of dy dt by dt. Clear?
Yes.
Clear or not?
Yes, sir.
What is this I0 into v by dt? Nothing but your I only, na? I by dt. Right? Okay. This is called your small signal resistance. Right? Sense. Fine?
Right.
Right? So now what will del I? Di is equal to small signal resistance into del V. Okay?
Okay. Okay.
Del V. What is small signal
So,
resistance equal to? Vt by I into del V. Tell me.
the dynamic.
Yeah, dynamics here. How much change in current is depending upon at what current you are in, what operating point. Because this R is dependent upon my current, right? So my change in voltage it will depend upon at what point you are in, at what current you are in. Like in this curve, suppose you are in this current ID1. Now this is your ID2. Okay. So if you go to ID1 to ID2, the change will be different. Getting?
Right, sir.
Yeah. So the change in current will depend upon
Temperature.
what operating point you are in. Yeah. Tell me.
And there also, it's also depending on temperature, right, sir?
Yeah, it will depend because it depend on VT, na? VT is there, so the R will depend on temperature.
Okay. Okay.
Okay. So if you want to draw the ID VD for different temperature, okay. If for temperature T1, if you go to temperature T2, it will be like this. When T2 is greater than T1, right? So even if you are in the same current, ID, okay, the slope of this curve is different from slope of this curve, right?
Right.
So the R will change, right? If you go to high temperature, the R should be increasing. Is nothing but VT. Clear?
Clear.
Okay. So this is my small signal approximation. Okay. So this question is asked in the exam. There is a VD, there is a ID. They change VD by a certain amount. They ask what is the change in ID. Okay.
Okay.
So this is the question. One last thing I want to cover before I leave. Okay. What is called diffusion capacitance? See theory. Actually, there are many things to cover. Okay. But I'm covering just to the things that is needed. Okay. Because for the time, in this time, you have to cover the maximum thing that is possible. Okay. So if you can go as detail you want. Okay. We're just giving you an overview of the subject. Okay.
Sure, sir.
Fine. So, like you have seen here, since if I change the voltage, right, the change of hole concentration, right, this is change of hole concentration, this is change of hole concentration, right or not? So this change will depend upon the my VD, right? So in neutral region also, I'm getting more number of holes and more number of electrons,
Right.
right? So since I'm getting more number of holes and more number of electrons, with by changing the forward bias voltage, so I will get a capacitance that is called diffusion capacitance. Fine.
Fine.
Fine. So diffusion capacitance means that this will occur in a forward bias. Okay, diffusion capacitance, okay, will be more means generally we have assumed that ki in diffusion capacitance this is in reverse bias. Okay, even if it is zero also, I have some same. I have derived using reverse bias. Okay, even if DR is equal to 0, okay, definitely there is some diffusion capacitance. Right or not?
Right, sir.
Even if it is forward bias also, there is some, it should be plus become minus. Okay, but the diffusion capacitance will not be 0. Okay.
Right, sir.
Similarly, here the diffusion capacitance is nothing but I mentioned you, if I increase current, if I increase the voltage, the injection will be more, the holes will be more. So there is change in charge carrier by change in external potential, that is giving me a capacitance that is called diffusion capacitance. Fine.
Fine.
Okay. Okay. So suppose I want to like suppose this is a P plus N junction. Okay. Right. So
Right.
P plus N junction means what I am assuming, this injection is far more compared to this injection. Okay.
Please.
Okay. So actually it should be C diffusion is equal to, okay, d of Qp plus Qn by dV. Okay.
Okay.
Qp is the excess minority carrier in what N side. Okay. Qn is the excess minority carrier in P side. Fine. Okay.
Okay. Okay.
What is Qp? Qp we know. So this is my action. Okay. Coming like this. Okay. So if you see the approximation, right, it will be my LP. Okay. So Qp will be, this is my del P. Qp will be approximately equal to charge into area into distance is LP, del P into LP. Clear? How? You see that actually del P is nothing but the total area under this one. Okay. I am approximating this area as this area. This is approximation. Okay. I am assuming this one is approximately equal to this. So I am approximately this area I am assuming as equal to this area. Right? So del P into LP is approximately nothing but the area under this exponential curve. Okay.
Okay.
Fine.
Fine.
Fine. Otherwise, you can take the exponential curve, you can do the integration. Okay. It will come approximately del P into LP.
Okay.
Okay. So now P diffusion equal to d by dV of QP nothing but QA into LP into LP. Fine.
Right.
Okay. Equal to QA LP into dP by dV. Right.
Right.
We know del P is equal to Cn0 into exponential of right.
Right.
Right. So what is d del P by dV equal to Pn0 by Vt. If I can neglect the one, okay, it will be equal to V0 plus Vt by exponential of Vt. Fine. Fine, na? Okay.
Right.
What is P0 in exponential of Vt? V by Vt equal to del P plus P0 equal to del P plus P0 divided by Vt. Okay. I don't know.
Right.
So now this is del P by del P. Okay. What is now C diffusion? C diffusion equal to A QA LP QA LP into del P by dV is nothing but del P plus P0 by Vt. Clear? Fine or not fine?
Fine. Fine.
Fine. Okay. So, but we know I is equal to, okay, if I approximately assume that key there is one charge junction, right? I am assuming that P is assuming ND is far ND is far greater than NA. Okay, for simplicity. Okay, so in that case, ND. So in that case, what will be my current? My current I is equal to I know how much it is QA, right? LP by LP into dp, right? Na? Okay, plus Q del N by Ln will be there, but I'm assuming that in ND very small compared to NA, so I'm just that part QA del N into dN by Ln. I'm assuming that very small. Okay, so that's why I can put 0. Okay, fine. Fine. So now you just multiply tau by tau. Okay, what is depend tau p? LP square. This is equal to LP square, right?
Right.
Or not?
Right.
Huh? Hello?
Right, sir. Right.
Then LP will cancel. LP by tau p. Okay. Now you put del p by this one. Okay, you put del p here. Okay. Now here we put I equal to Q A L P. What is del p? So this del p plus P n 0 equal to almost equal to del p only, right? So I'll put del p here. I into tau p divided by Q A L P into Vt. Okay. This got cancel. I got I into tau p by Vt. Fine.
Fine.
So this is my diffusion capacitance, which is proportional to the current that is flowing. Okay.
Okay.
And which will be significant in forward bias. In reverse bias, it will be very small. Right or not?
Right.
So if I cannot ignore the current due to electrons here, like if it is in a simple, if it is not a, if this condition is not true, okay, if both electron and holes are there, okay, so this will be C diffusion will be equal to IP0 into tau P0 plus I10 into tau 0 by 250. Okay, if it is not a P plus N junction. Okay, heading
What VT is the denominator? 2 VT.
2BT is this one. The BT is below 2BT. If both electrons and whole quantity will be there.
Okay.
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 Okay. So this is my diffusion current. So the summary is the diffusion current proportional to the forward bias, nothing but a current.
Okay.
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 Now, if I want to do the small signal representation of the final, okay, just last minute, small signal model of diode, right? So we know, right, diode, we have a resistance, right? I showed you R is equal to Vt by I, I do not, okay?
Right.
Also, we have got a capacitance, see diffusion equal to I into tau I Vt, okay? Also, you got one, see depletion. Okay. Okay. So this is the small signal. Yeah, tell me.
Can this C diffusion and depletion represent the same figure because it's
What?
one is in forward bias, one is in reverse bias. So
No, that's no, nothing like that, right? I told you in reverse bias, this will not be, this will be very, very small, approximately 0. This will be there. In forward bias, anyway, it is there. Depletion will be there, and this all both will be there. Depending upon the region, some will be small, some will be bigger.
okay.
Okay. Okay. So this is my end of my diode. Okay. So in diode, what you have understood? You have understood diode PN junction in equilibrium. Okay. In equilibrium, what are the things you covered? You covered built-in potential. Okay. Built-in electric field. We have got depletion width. Right. All the things you have covered. Right. Also, you have seen the energy band diagram. I don't know.
Right.
So then in forward wise, what thing you covered? In forward wise, you tell me. Hello. Hello.
Hello.
Tell me.
The last slide once again. Yes.
Huh?
Can you see the last slide once again?
Last slide not visible?
Last slide.
Yeah. Tell me.
Just take it out.
Which one?
Okay.
Fine, na?
Fine.
Yeah. So I'm telling what these things we have covered. Okay. Then we have in forward bias we have covered the carrier profile. Okay. We have covered how
Okay.
the current flows, current profile. Right.
Right.
We have analyzed the electric field, BI. Okay. All the things you have seen in forward bias. Okay. In reverse bias, we have seen how the current flows, and also we have seen C depletion capacitance, right?
Right.
How the HD will become, things we have seen. Okay. Also in forward bias we have seen C diffusion. Okay. We have seen the small signal equivalent, resistance. Okay. I don't know.
Right.
Right. So almost all the things you have covered from the diode. Okay. From the physics point of view. So all things is clear to you, na? Very much.
I have one.
Pardon me.
I had one doubt in that reverse bias thing.
Tell me. Which slide?
By previous the reverse bias.
Yeah. Here, na?
And the diagram was there that weird diagram.
Here.
Maybe okay, it's okay. So if we take the depletion region,
Actually, voice is not coming properly.
Is it audible, sir?
Now audible. Tell me.
If we increase the reverse bias voltage,
Huh?
that the junction depletion width will increase.
Yes.
So, what is the point? If we increase more and more, then the depletion region will reach the contact area. That
See,
kind
see,
of.
see. Then that you need very, very high potential. Okay. So for that you are telling ki to go on increasing it, this will go to contact area, right? That
Okay.
need very, very high potential. Very high potential. Okay. You take a example. Okay. You take an example like we have shown. You just know what is XD. Okay. XD you know proportional to VBI plus VR. Okay. You do a mathematics. What is the value of VR is needed? Okay. To complete deplete the this region. Okay. This is a question I think came in 2020 or 19 or 22. Sorry, 2021 or 2020. Okay. Out of see, get 2020, 2020. I have solved the question. Okay. You see this, you go to the IGC website. Okay. You can see 2021 or 20 or 19. So in this in this 2 3 year, question have come. And what potential is needed, right? To complete deplete the reverse bias. Okay. What is the reverse bias needed? To completely deplete this region. We proportional to VR. What is the VR is needed to completely deplete this region? This is the question that have come in the exam.
After that, the device get damaged or something.
No, it won't damage. See, it won't damage. So if it will come here, right? It won't damage. Why it will damage? So then if you come here, then whatever suppose if you increase reverse bias, right? It will fall in this contact only, because already almost all the things you have covered, right? Now suppose this is also uncovered, right? Now completely depleted. Then whatever extra potential you will apply, right? It will fall in the contact.
Okay, okay.
Getting?
Right, sir. It's behaves like
Also, if you see one more thing which I did not cover, there is something called breakdown. Okay, there are two phenomena. One is called general breakdown. General. One is called avalanche. Okay, there are two phenomena. So if you go on this, see what is the maximum reverse bias potential? You are diode. Okay, that is nothing but reverse blocking capacity. Okay, VR cannot be anything. There is a blocking capacity. There is critical electric field. Okay, so if you study what is the general breakdown, what is the avalanche breakdown, okay, it will take place in the diode. So if you go on increasing the VR, right, at a certain point, this diode will break down, then a huge current will flow. Okay.
okay.
Because if you increase this potential, the electric field will increase. Okay, a point will come, the completely this breakdown will occur. There will be a huge number of carriers generated in the depletion region. There will be huge current. Okay, this part is called breakdown mechanism. Okay, so that I did not cover actually the breakdown mechanism.
Okay. Sir, so after uncovering all the carriers, then only the breakdown happens, or in
No. This breakdown is different. Okay, the breakdown is this is uncovering possible. Okay, but
Okay.
this breakdown what I'm telling is a different thing. Okay, before this only this will take place. How it will take place? You go and read this general breakdown and avalanche breakdown. Before reaching this limit also, this device will break down and huge current will flow.
Okay, okay. So
Okay,
it depends
did
on
not
the
to reach this one.
material.
Okay, it did not to reach this one. Okay, before this only it will happen.
Okay, so it depends on the material, maybe, right, sir?
It's not material. Yeah, it's depend upon some part of construction also. Okay, not material actually. It's a construction. Okay, construction means doping. This out of these two, right? General devalence. There are two kind of mechanism. Okay, the general dots are made specially. Actually, doping is the one important parameter. Okay, so the PN junction will be doped in such a way that in one diode general will take place, another diode devalence will take place. Okay, so
Okay.
but thing is, if I will, if I will have time, right? in future classes, I can cover these two things, general and balance. See, if I get two classes, right? Two classes. So one class is coming to BJT. Then if I time permit, you make me recall, I will cover this breakdown mechanism.
Okay.
Fine.
Fine.
So this depends upon doping, not the construction. Okay. Which mechanism will take place.
Okay.
Doping also, the material also, like the depend upon the energy gap. Material also it depends.
Okay.
Okay, both material and doping. Fine.
Fine.
Is there any question?
Nothing else.
Okay. This things which you covered is very clear, very much clear to you.
Clear.
Okay. Now you are confident.
Huh?
Now you are confident.
Yes, sir. Yes.
Okay. Good. So then we shall stop this class here. Okay. See you in next class. Fine. Okay. Good night.
Good night, sir. Good night.